All right, on to a bunch of examples where we practice with using Newton's law of gravitation to solve problems. Number one, a bowler trying to knock down a 2.5 kilogram bowling pin releases his 5 kilogram bowling ball at the end of the lane, 20 meters away. As he releases the ball, what is the magnitude of the force of gravity between the ball and the pin? So since we're talking about the ball and the pin, we can't use Fg equals mg. Neither of those is the Earth. We must use Fg equals g m1 m2 over r squared. That looks like a 6, I apologize. It's a g. G, big G, is 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared. M1, let's make that the bowling pin, 2.5 kilograms. M2 is the ball, 5 kilograms. Does it matter which one is which? Absolutely not. End of the lane is 20 meters away, so that means the bowling ball and the pin are 20 meters apart. So we do 20 meters squared. 6.67 negative 11 times 2.5 times 5 divided by 20 squared. Let's see. So divided by, in parentheses, 20 squared is 400. And the parentheses, that means we're going to divide what we had initially by 400. We end up with 2.08 times 10 to the negative 12th newtons for the force of gravity. If the bowler had used a lighter ball, 2.5 kilogram bowling ball, instead, how would the force of gravity be different? Prediction would be it will be less, but how much less? I could go back and I could go through and do the math all over again, replace this with 2.5, but I'm going to do this algebraically instead. The 2.5 kilogram bowling ball implies to me, let's see, that was, the bowling ball was M2, so that means that this M2, I'm going to put M2B as a subscript, is, let's say, 1/2 of the initial M2. I should be able to plug that right in to my force of gravity equation. So I'm going to write FGB equals G M1 M2B over R squared. Nothing changes except for M2B, therefore FG might also change. So this is going to be G M1, and then that's going to be times 1/2 of the original M2 over R squared. I'm going to bring that 1/2 all the way to the front, so I have 1/2 times G M1 M2 over R squared. This is just equal to my original Fg. And so we do see that the new force of gravity is 1/2 of the old one. So 1/2 times 2.08 times 10 to the negative 12th newtons gives us a new force of 1.04 times 10 to the negative 12th newtons. And again, notice how small that force is because we're dealing with everyday objects. The force of gravity between everyday objects is very, very, very small. It's still there, but it's very small. C, when the 5 kilogram ball is 3/4 of the way to the pin, how has the force of gravity changed? Well, 3/4 of the way to the pin means that the bowling ball is now 5 meters away because it's gone 15 of the meters between the bowling ball and the pin. So I wouldn't write 3/4 in for the change for R. I would say that since it's now 5 meters away, R, I'm going to write C, is 1/4 as big as it used to be because 5 is 1/4 of 20. FGC, and you can make these subscripts whatever you want. I'm just making them so that hopefully I don't confuse myself, equals G M1 M2 over RC squared. I know RC is 1/4 of the original R, so I'm going to write G M1 M2 over, in parentheses, 1/4 R. That whole thing is getting squared. Again, I can't just write 1/4 R squared without parentheses because that implies that I'm going to square the original radius and then take 1/4 of it. That is not the same thing as acknowledging that the radius itself is smaller and that whole thing has to get squared. So this will be G M1 M2 over 1/4 squared is, let's see, 1 squared is 1, 4 squared is 16. So this should be 1/16 R squared. Now, 1/16 on the bottom is a little weird. There's a trick you probably learned in math class at some point that if you have a fraction in the denominator of another fraction, you can rewrite it as the reciprocal in the numerator. So instead of keeping it like this, I'm going to change this to 16g m1 m2 over r squared. If you don't believe me, that you can make that change. Dividing by a fraction is the same as multiplying by its reciprocal. So for instance, if I do 10 divided by, in parentheses, 1/16, I get 160, which is the same as 10 times 16, 160. This is the original FG, 16 FG. So by quartering the distance, the force of gravity between the two objects is 16 times as big, which means it's 16 times 2.08 times 10 to the negative 12 newtons. Still going to be very small, but it is bigger than it was previously. In this case, 3.33 times 10 to the negative 11th newtons. Okay. Next little set of examples. What is the force of gravity between a 60 kilogram person and the Earth? Okay, so right away we could set up our equation. Fg equals g m1 m2 over r squared. G is 6.67 times 10 to the negative 11th. Newtons times meters squared over kilograms squared. Let's make m1 the person, so there's 60 kilograms. And Earth's mass, I'm going to have to squeeze it in here, but the mass of Earth is 5.98 times 10 to the 24th kilograms. 5.98 times 10 to the 24th kg. And that's over, well, what's the distance between the person and Earth? Here's a really not to scale version. Here's Earth. Here's the person. You might be tempted to say that there's no distance between them, but remember, when we talk about the distance, we're talking about the distance between centers. Here's the center of the person, which is basically at the surface of Earth compared to the size of the Earth, and here's the center of the Earth. To me, that looks like one Earth radius. There's an Earth radius between the person's center and the Earth's center. The radius of Earth is 6.37 times 10 to the 6th meters. So that is what we're going to plug in, and that is what gets squared. 6.37 times 10 to the 6 meters squared. Force of gravity between the person and the Earth is approximately 589.8 newtons. Okay, so decent size because even though the person's small, Earth is very big. Now, you might be wondering, if you're very perceptive, why on earth did I just do all that? I'm asking for the force of gravity between a person and the Earth. If Earth is one of your objects and the other object is very clearly on Earth, then we can just use this, Fg equals mg. Let's see if we get the same answer. Person's mass is 60 kilograms. Little g is the acceleration due to gravity. Doesn't mean the person's accelerating, it's just a constant we use in this equation. 9.81 meters per second squared. 60 times 9.81 gives us 588.6 newtons. Now, it's not exactly the same because there's some rounding that's going on both with this number and with some of these numbers. And in addition, there's like one other very small effect that is happening. But those numbers are practically identical. I mean, they're less than 1% off. They're identical for all intents and purposes. So just remember that you don't always have to use gm1m2 over r squared. If you're asked about the force between two objects, and one of them is the Earth, and the other object is very clearly on the surface of Earth, or very close to the surface of Earth, then you can just use Fg equals mg. For any other case, though, you have to use the extended version, the Newton's universal law of gravitation. All right, so let's move this up a little bit. Okay. If the gravitational force is the only force acting on that person, determine the gravitational field strength of Earth at that point. When you see this phrase, gravitational field strength, what that means is basically find the acceleration caused just by gravity. Okay? So essentially, what we're looking for here, just notice that whenever we talk about acceleration due to gravity, another word or phrase for that is gravitational field strength. So basically, how much are they accelerating if the gravity is the only force on them? If gravity is the only force on them, that means it's the net force. And anytime we have a net force, we know it's equal to ma. The force of gravity, let's use the first one, 589.8 newtons. The person's mass is 60 kilograms. If they're in free fall, then their acceleration would be 9.83 meters per second squared, which is basically 9.81. Again, we're talking about less than a % difference. All right. So due to rounding and other smaller factors, the other factor is Earth's rotation actually plays a part in this, but it's a very, very small part. This is basically your 9.81 meters per second squared. So that's what we should expect. If the gravitational force is the only force on you, that means there's no normal force, no applied force, none of that stuff, then that means that your acceleration in that case, or this person's acceleration, is basically the acceleration that we get when something is in free fall. So that totally makes sense. What about the Earth's acceleration? Let's assume that the only force on Earth is this force of gravity from the person. So there's only one force acting on Earth, and it's the force of gravity from this person. We still set this up the same. The only difference is the mass of Earth is going to replace the mass of the person. The Earth is getting a force of 589.8 newtons put on it because of the interaction between Earth and the person. So remember, Newton's third law says the Earth and the person are exerting equal forces on each other. 5.98 times 10 to the 24th kilograms is the mass of the Earth. And we're solving for the acceleration of the Earth now. And we get 9.86. So pretty much the same thing, but not really the same thing. Look at that exponent. 9.86 times 10 to the negative 23rd meters per second squared. That's tiny. Basically imperceptible, probably imperceptible. So does it exist? Absolutely yes, the math says it does. Is it something that will ever necessarily affect the Earth to any great degree? No, not at all. So you are pulling the Earth towards you. You do cause it to accelerate towards you, but it's a tiny, tiny, tiny acceleration. Okay, moving on to a different set of problems. Find the magnitude of the force of gravity between the Sun and the Earth if the mass of the Sun is 1.99 times 10 to the 30th kilograms. All right, this is straightforward calculation. Fg equals G m1 m2 over r squared. G is 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared. M1 will do that mass of the Earth, 5.98 times 10 to the 24th kilograms. Mass of the Sun, 1.99 times 10 to the 30th kilograms. And we need the distance between them. This is listed in the reference tables. It's kind of funny. The distance between, or the mass of the Sun is not listed in the reference tables, but the distance between the Sun and the Earth is. Mean distance, Earth to the Sun, 1.5 times 10 to the 11th meters. And remember, that whole thing has to get squared. We see that the force between the Earth and the Sun is 3.53 times 10 to the 22nd newtons. That's, I think, about 350 or at least 100. Let's say at least 2 orders of magnitude bigger than the force between the Earth and the Moon, if I'm remembering correctly. Let's Let's check that real quick. Just out of curiosity. Yeah, about 2 orders of magnitude bigger. Okay, so there's the force between the Earth and the Sun. How would the force change if the Sun were 3 times as far away? So, if the Sun were 3 times as far away, I'm going to call that R1 would be 3R. R was the original distance between Earth and Sun. R1 is now 3 times as big as R. FG1 equals G M1 M2 over R1 squared. G M1 M2 over, in parentheses, 3R squared. I got to square what's in parentheses. It comes out to be G M1 M2 over 9R squared. The original force of gravity, G M1 M2 over R squared, is Fg. We've got a 9 on the bottom, so this is equal to 1/9 the original force of gravity. The original force of gravity was 3.53 times 10 to the 24th. Wow. Okay. So I take it back. It's like 10,000 times bigger. Excuse me. Oh, wait a second. Let me double check some math here. 6.67 times 10 to the negative 11 times 5.98. Apologies for that, guys. Okay, it was to the 22nd. All right, my bad. And then, okay, so this should be to the 22nd. Ah, I know. Wait a second. Okay, I see what happened. So 3.53 times 10 to the 22nd newtons. I need to multiply that by 1/9, which is the same as dividing by 9. And that gives me 3.92 times 10 to the 21st newtons is the new force of gravity. I think I read my 1 as a 4 on my notes here. Okay, so what would that's how the force would change if the Sun was 3 times as far away. Going off of this again, how much would the force change if the separation between Earth and Sun was normal, but the Earth was 5 times more massive? Oh, I gotta move this down. But the Earth was 5 times more massive. Okay, so I'm gonna call this M. Let's see, Earth was M1, so I'm gonna call it M1A is now 5 times the original M1. It was M1, right? Yes, it was. Okay, so FGA equals G times M1A, M2, R squared. M2, the mass of the Sun, and R, the separation distance, are normal. M1, the mass of Earth, is the only thing that we are changing right here. So this is going to be G. I'm going to substitute 5M1, M2 over R squared. Bring the 5 out to the front. We get 5G M1, M2 over R squared. Gm1 M2 over R squared is our original force of gravity. So this is 5 times Fg. The original Fg is 3.53 times 10 to the 22nd newtons. Which gives us 1.76, that 5 shouldn't be there, times 10 to the 23rd. That's just a relic from rounding, is the new force of gravity. Just like we expected, because we increased the mass, therefore we increase the force of gravity. We expect the force of gravity to increase as well. All right, 8, what is the magnitude of the Earth's acceleration due to the force of gravity on it from the Sun? So how much is the Earth accelerating? Again, just like before, we're going to assume that the only force acting on the Earth is the force from the Sun. So F net equals Fg equals ma. Any F net is always equal to ma. The force of gravity on the Earth, let's go the original force of gravity, the actual, 3.53 times 10 to the 22nd newtons equals 5.98 times 10 to the 24th kilograms times A. And it turns out that the sun causes the Earth to accelerate. And it accelerates at a rate that's actually a little bigger than you probably think, even though it's really far away. 0.0059 meters per second squared. Now, what does that mean? That's like 6 or so millimeters per second every second. And if you think about the definition of acceleration, you might be like, so does that mean the Earth is speeding up? Or does it mean it's slowing down? What's happening? It actually means neither of those. What this is, and we'll talk about this in the next little mini topic, it's another little mini forces topic. This is not a speed up or a slow down acceleration. This is an acceleration that has to do with the changing of direction. Because remember, the Earth is going around the sun. So we'll come back and talk about this later on. Last, or second to last set of examples. A spaceship is flying above an alien planet. The distance from the planet's surface to the spaceship is equal to the planet's radius. How much smaller is the gravitational attraction between the spaceship and the planet as it flies, as compared to the gravitational attraction between the spaceship and the planet if the spaceship was on the ground? So let's look at a picture of this. We're going to draw this as when the spaceship is on the surface. Okay? When it's on the surface, here's the planet's radius. We know that at this point, Fg, the force of gravity between them, equals G, m1, m2, mass of the spaceship, mass of the planet, over r squared, where r is the distance between the spaceship and the center of the planet. What we're talking about now is when the spaceship is flying, it's flying a distance of 1r above the surface. Okay? So, you can see here that the distance has doubled. I'm going to call this Fg1 equals G, m1, m2, and we now have r1 squared. And I know that r1 is 2 times the original radius. So you can probably see where this is going already. But 2 times the original radius means that we're going to have an extra 2 in the bottom here, and that's probably going to decrease the force of gravity. Remember to put that in parentheses so you can square the entire thing. This becomes G m1 m2 over 4r squared. 1/4 the original force of gravity. And since there's no other numbers, that's our answer. This is just saying how much smaller is the force of gravitational attraction between the spaceship and planet as it flies, as compared to the gravitational attraction when it's on the ground. The force of gravity is 1/4 as big. Okay? And that makes sense. The two objects that we're concerned with are now farther away from each other. Okay, this is the second to last set of examples. I forgot that 9's kind of separate. If an astronaut on the ground has a weight of 800 newtons, what is his weight when he is 3 Earth radii away from the center of the Earth? So we're going to draw some more pictures here. Here's Earth. Here's the radius of Earth. And here's our astronaut. We're going to say he's standing right here. Okay? At this point, Fg equals G, m1, m2, over r squared, and we don't know the exact numbers, but his weight is 800. We want to know what his weight is when he's 3 Earth radii away from the center of the Earth. So Earth is still here, this is still the radius of Earth, but he's 3 of these radii away. Hopefully with a spacesuit on. Okay? So again, we're changing the distance between the objects. So now we're going to say R1 is 3R. Fg1 equals G m1 m2 over R1 squared. G m1 m2 over, in parentheses, 3R squared g m1 m2 over 9 r squared. This is just the original force of gravity times 1/9. So this is Fg1 is 1/9 the original force of gravity, which we knew was 800. 1/9 times 800 newtons is, or 800 divided by 9, 88.9 newtons. So the astronaut gets farther away, his weight goes down. Now read number 11. It sounds like almost the exact same problem. What is the astronaut's weight when he is 3 Earth radii away from the surface of Earth? So at first glance, it looks like the same problem, but I'm going to underline 2 words that show that it's different. In 10, we were talking about 3 Earth radii from the center. In 11, we're talking about 3 Earth radii away from the surface of Earth. What would that picture look like? That picture would look like this. Here's Earth. If he's 3 Earth radii away from the center, it's this far. But this is only 2 Earth radii away from the surface. 3 Earth radii away from the surface means that that astronaut is farther out. Okay, you can see right there that he's farther away. So I'm going to label this R2 this time, and we're going to say that he's now 4R, 4 Earth radii away from the center. 4 times as much separation as up here when his weight was 800. So Fg2 is g m1 m2 over r2 squared. We established r2 was 4r, so this is going to be g m1 m2 over, in parentheses, 4r squared. So g m1 m2 over, this will turn into 16r squared. Fg2 is 1/16, because the 16 is on the bottom of the original Fg, which means it's 1/16 times 800 newtons. 800 divided by 16 is 50 newtons is the force of gravity. So you have to read very carefully to see in questions like this if it's from the center or from the surface. Okay, and it makes sense. He's farther away. The force of gravity keeps going down even more. Last question. There's no numbers at all here, and this is actually a very common type of question on the Regents. The force of gravity between 2 stars in a binary star system is F. In terms of F, meaning your answer should be a coefficient in front of an F, what would the force between the stars be if both doubled in mass and the distance between them tripled? So we're saying that the original force, obviously we're talking about the force of gravity between these 2 stars, would be dependent on, well, the universal gravitational constant, the mass of both stars, m1 and m2, and the distance between them. Now, both of the stars double in mass, so m, I'm just going to call it a, for both equals 2m. And the distance between them tripled, so I'm going to call it Ra is 3 times the original. So Fa would be equal to g m1a m2a over Ra squared. This would be g 2m1 2m2 over, in parentheses, 3r squared. I can treat the top and the bottom separately. I can bring these 2's out to the front and multiply them together. That'll give me 4g m1 m2. This whole thing on the bottom will turn into 9r squared. And so we see that Fa will turn into 4/9 the original. Okay, force of gravity, if these changes were made, even if the mass increases by this much and if the distance triples, the new force will be 4/9 the size of the original. This is a very common way of doing these questions. Okay, you will get questions that look like this. Really, all you're doing is you're looking for how the how the variables change by what factor. That's actually it for gravitation. We'll practice with this for a little bit, and then we'll come back, and our next unit will be on circular motion. Talk to you then.